In mechanics, a deceptively simple problem has been widely proposed in online lessons, school Olympiads, and university tests. It involves finding the frequency of small longitudinal oscillations of a spring with finite mass and stiffness, attached to a wall at one end and a body of mass m at the other, on a horizontal plane with negligible friction. The commonly accepted solution to this problem is flawed, as it neglects the kinetic energy of the spring itself. This misconception arises from considering the total kinetic energy of the system as T equals 1/2 mu squared plus 1/2 m3 u squared, where u is the speed of the body, m is the mass of the spring, and L is the length of the undeformed spring. However, this expression leads to an incorrect calculation of the system's oscillation frequency. The correct approach involves calculating the kinetic energy of the spring by integrating the kinetic energy of each point along the spring, resulting in the correct total kinetic energy. T equals 1/2 mu squared plus 1/2 m3 u squared plus 1/2 m4 u squared. This yields a different expression for the oscillation frequency, which takes into account the mass of the spring. The problem is solved using the Lagrange equations of the second kind for two scenarios. A. The spring lies on a smooth table, and B. The spring is attached to the ceiling. In both cases, the correct frequencies of small oscillations are derived, highlighting the importance of considering the spring's kinetic energy. Ultimately, the solution to this seemingly simple problem is non-trivial and requires careful consideration of the spring's kinetic energy. This research underscores the need for precise calculations and a thorough understanding of the system's dynamics to accurately determine the oscillation frequency. In the realm of physics, the oscillation modes of a spring with an attached body have been subject to significant scrutiny. Traditional solutions often neglect the mass of the spring in comparison to the attached body, resulting in only one oscillation frequency being considered. However, this approach is incomplete as there should be an infinite number of oscillation modes present. To address this limitation, the paper formulates the wave equation for unidimensional oscillations of an elastic medium, represented by equation 2. This equation describes the deviation of a point in the spring from its equilibrium position at time t, denoted as x, y, t. The speed of sound within the spring, c, is determined by the spring's mass m and stiffness k, as shown in equation 3. The author then derives the equation of oscillations using a discrete model, where the spring is represented as n balls interconnected by springs. This leads to Newton's second law for the motion of each ball, given in equation 4. By assuming that n is large and applying a Taylor series expansion, the author obtains the wave equation 2 and the boundary condition 6 for the motion of the attached body. The boundary condition at the fixed end of the spring is given in equation 7. The primary objective of the paper is to find the frequencies of small oscillations by solving the wave equation 2 with boundary conditions 6 and 7. This approach allows for the determination of an infinite number of oscillation modes, which form a complete set of functions enabling the solution of spring motion under arbitrary initial conditions. This refined understanding of spring oscillations provides a more comprehensive and accurate representation of the physical phenomena involved. The authors derive the wave equation solution as a standing wave, characterized by amplitude _j and phase alpha_j, where phi_j is related to the frequency omega_j through phi_j equals omega_j, c. The dispersion equation, 9, is obtained from the boundary condition, 6, which depends solely on the mass ratio Q equals m and is independent of K and L. This equation yields an infinite number of solutions phi_j, corresponding to frequencies omega_j proportional to phi_j Rk. Analysis of two limiting cases for Q reveals distinct frequency relationships. For Q much less than 1, phi_0 equals square root Q and phi_j greater than 0 equals j pi plus Q, j pi, resulting in omega_0 equals Rk, m, and omega_j greater than 0 equals j pi Rk per meter, omega_0. Conversely, for Q1, phi_j equals j pi plus pi 2 1 1 Q, leading to omega underscore j equals j pi plus pi 2 rk per meter. Notably, the ratio R equals omega underscore 0 per ohm is approximately equal to 1 for Q, much less than 1 in pi 2 square root 3 for Q1, indicating that omega underscore 0 and omega are nearly identical for all values of Q. This relationship is visualized in Figure 2, which demonstrates the connection between omega underscore 0 and omega across varying Q values. The requirement of an infinite number of frequencies to solve the problem with initial conditions x, y, 0, equals x, y, and x, y, 0, equals v, y, is also discussed. This analysis provides a detailed understanding of the frequencies involved in the system, highlighting their relationship with the mass ratio Q and its implications for the system's behavior. A spring with mass m attached to its end, subjected to a periodic external force F, T, equals F0 cos, omega T, exhibits complex vibrational behavior. The authors derived the equation of motion for this system and solve it using Fourier series decomposition, revealing that the solution x, y, t, can be expressed as an infinite sum of terms, each representing a distinct mode of vibration. The coefficients A underscore j and B underscore j are determined by the boundary conditions x, y, and v, y, respectively. In the case where the spring is slowly stretched to a length L and then released, corresponding to x, y, equals Li, L and v, y, equals 0, the authors demonstrate that higher modes are not excited when the quality factor Q is much less than 1, whereas all modes are excited but with decreasing amplitudes when Q is much greater than 1. The energy in each mode is calculated using a discrete model, resulting in the expression E equals sigma, epsilon underscore j, where epsilon underscore j depends on phi underscore j, A underscore j, and B underscore j. This analysis provides valuable insight into the vibrational behavior of the spring mass system under varying conditions, highlighting the critical role of the quality factor in mode excitation. When a body is attached to a spring and subject to forced oscillations, the equations of motion can be derived, as shown in equation 24. At specific frequencies, the amplitude of these forced oscillations tends to infinity, indicating resonance, which is demonstrated in equation 25. A detailed analysis of the resonance solution reveals that when the frequency of the external force matches one of the natural frequencies of the system, the amplitude of the oscillations increases linearly with time, as shown in equation 26. Alternatively, when the spring is attached to the ceiling, as depicted in Figure 1b, the equations of motion take a different form, presented in equation 27. The stationary solution for this setup is given by equation 28. Notably, by making a substitution, it can be shown that the frequencies of small oscillations in both setups, A and B, are identical. This analysis provides insight into the dynamics of a body attached to a spring under forced oscillations, highlighting the phenomenon of resonance and its implications for the system's behavior. The equivalence of the frequencies of small oscillations in both setups underscores the significance of this research in understanding the underlying mechanics of these systems. This research presents a novel solution to the oscillations of a massive spring with a finite mass body attached, countering intuitive assumptions and highlighting the importance of rigorous analysis in understanding physical phenomena. By building upon established principles of solid-state physics, as outlined in J. M. Siemens' Principles of the Theory of Solids, the study demonstrates that complex systems can yield novel insights when examined carefully. The analysis challenges seemingly obvious assumptions, underscoring the need for a meticulous approach to understanding physical systems. The work's conclusions reinforce the significance of rigorous examination, as exemplified by the example of the massive spring with a finite mass body. This research serves as a testament to the potential for groundbreaking discoveries that can emerge from the thorough investigation of complex systems. The study's findings have significant implications for the field, emphasizing the importance of careful analysis and the potential for novel insights from complex systems. By providing a non-trivial solution to the oscillations of the massive spring, this research contributes to a deeper understanding of solid-state physics and its principles. Ultimately, the work highlights the need for continued rigorous analysis and examination of complex systems, with the potential to reveal new and unexpected insights.